Hello everyone. My name is Velitchko Filipov, and today I will be presenting our invited state-of-the-art report on network visualization, titled Are We There Yet? A roadmap of network visualization from surveys to task taxonomies. A brief outline of this talk. I will introduce what network visualization is about and present the motivation behind this meta-survey. Then I will discuss our proposed roadmap and different disciplines in network visualization. I will talk a little bit about task taxonomies for network visualization and their coverage across different disciplines. Finally, conclude the talk by outlining open challenges and summarizing our research. We start with an introduction of network visualization and provide the motivation behind this survey. Networks are ubiquitous structures that broadly model a set of entities or data points and the relationships between them. These can be represented as a set of vertices and a set of edges defining the links between them. Due to their abstract structure, they can be used to model many problems and, therefore, have been employed in a wide range of applications across multiple domains. The aim of network visualization is to develop effective and meaningful representations in order to support a broader understanding of network data, foster insight generation, and detect unexpected patterns. The field of network visualization is rapidly expanding and focusing research on increasingly challenging topics, such as the visualization of dynamic, multivariate, large, and geospatial networks. However, research in these various topics is scattered, often having inconsistent terminology and classifications. There is also a lack of task taxonomies that are sufficiently expressive for their type of data for most topics. Over the last few decades, we've seen a transition from standard and popular network visualization approaches to more complex and intricate ones. This results in a wealth of visualization techniques that target specific problems. However, when surveying network visualization in its entirety and considering all the different branches, there is no comprehensive overview. For researchers and practitioners surveying this domain, it can get overwhelming very quickly when exploring the larger field of network visualization. They may lose overview when drilling down into the individual branches of network visualization tackling very specific problems. They may find themselves asking questions such as, how can I contribute? What problems are there still left to solve? Has this already been done? We think that there is a need for a quantum step in survey literature on network visualization, so that we may be able to answer questions such as, what has already been done? What are areas in the domain that have yet to be explored? This led us to writing a meta-survey on the topic. All these questions and challenges led us to believe that there could be a better way to survey network visualization, so that we can go from feeling overwhelmed and lost to navigating this domain and finding our way. Our main goal with this work is to provide a roadmap that details the relationships between different branches of network visualization and outlines opportunities for future research. Our research methodology is made of multiple refinement cycles, where we incorporate aspects of the PRISMA statement, specifically outlining inclusion and exclusion criteria for the review, specifying information sources and search strategies, presenting the main outcomes, contributions, and open challenges for each, and outlining limitations. We started our literature review with a small set of surveys that were previously known to us, and we expanded this by performing forward and reverse lookups citing or cited by. Furthermore, we queried multiple search engines for combinations of keywords including survey, state-of-the-art report, taxonomy, design space, and graph and network visualization. This process resulted in 43 publications after our filtering and inclusion criteria. This was from an initial set, with a total of 152 publications that we gathered in a spreadsheet. We excluded publications that did not have a contribution in the domain of visual analytics or visualization or were out of our time window of interest, 2000 to 2021. Here you can also see a breakdown of the amount of papers we found in each venue, the most being in CGF and TVCG. The other category groups together all venues that had one publication each. Surveys represent a practical way to summarize a volume of papers in a given field. Our inclusion criteria for surveys meant that each publication needed to meet the following characteristics. The publication is a systematic review of literature about a specific network visualization discipline, providing a categorization of a broad selection of approaches. The focus of the survey is strongly oriented towards network visualization and has a clear contribution in this domain. Taxonomies enable preparing common benchmark tasks that guarantee fair evaluations and comparison across different visualization techniques. They can be used to bootstrap developing new approaches or comparing existing ones. The taxonomies that we include fulfill the following criteria. The publication provides a selection and categorization of possible tasks that can be applied for network visualization to extract information and/or insights. Taxonomies can be obtained, for example, through interviews and user studies, or by extending existing higher-level taxonomies and adapting them to support data types specific to a network visualization discipline. Taxonomies are evaluated either empirically or through a theoretical treatment. In our work, disciplines refer to branches of network visualization that deal with specific data types. The networked nature of the data is common among all disciplines. Each discipline is enriched with attributes and dimensions, for example, dynamic, multivariate networks. To consider a branch of network visualization as a discipline, it should fulfill the following criteria. The branch of network visualization should have at least one survey discussing and categorizing techniques specifically designed for it. Maturity. The data type should have unique properties besides the networked nature of the data that are not covered in other disciplines. Specificity. Our work is inspired by the idea of a meta-survey. There is some related work on the topic of meta-surveys. The meta-survey on information visualization surveys draws a landscape of information visualization literature through 86 survey papers classified using the information visualization pipeline. The meta-survey on text visualization catalogs 13 surveys into 5 categories, obtained based on the main focus and themes found in each. The meta-survey on interpretation of machine learning models catalogs and discusses 18 surveys about the use of visualization explaining these models. In the following, I will present our roadmap and the disciplines that we identified from literature along with their relationships and characteristics. We propose a roadmap of network visualization to assist researchers in orienting themselves in this field. The same way that a roadmap is generally used to plan a journey, our roadmap is designed to guide and support researchers in finding inspiration, novel research directions, or appropriate task taxonomies for their evaluations. We group surveys and task taxonomies into non-overlapping sets, based on their discipline. These are represented as nodes with a heading and gray border. The disciplines can build on each other into diverging directions or can be specializations of one another. We model these relationships as directed inheritance relationships that can be seen as roads that lead from one network visualization discipline to another. The green road signs indicate how the data and its characteristics changes when traveling from one discipline to another. In the following, I will present the disciplines we identified and explain how they are connected to each other, considering the characteristics of the networked data being visualized. I will use a more schematic representation of the roadmap for simplicity, and the current discipline and roads to it will be highlighted in red. First off, we have general network visualization, which refers to a set of techniques that address the problem of visualizing simple networked data, a set of nodes and their relationships. The main focus of this discipline is to provide methods of visually representing a network, such as node link diagrams, matrices, contact graphs, alternative and / or hybrid approaches. The visualization techniques in this discipline typically tackle challenges such as how to produce effective layouts of the graph, improve the visual scalability, which aesthetic criteria to prioritize for the drawing. Moving on to large network visualization. This extends general network visualization to represent networks with a large number of nodes and / or edges. The notion of what a large network is changing over time. In the early 2000s, a large network was considered to have thousands of edges and nodes, whereas nowadays, we have networks exceeding millions. Another way to arrive to this discipline would be through group network visualization, when we consider aggregation, grouping, or clustering as effective methods to represent large networks. In this case, they provide an abstract view of the network and scale better. Group structures in networks are a subset of nodes, where each subset has some characteristic in common in order to warrant a grouping. In this case, we can reach it by starting from general network visualization and considering what the grouping strategy for the nodes may be. These groups can be either disjoint or overlapping, meaning, if a node belongs only to one or multiple groups. Groups can also be unstructured or structured, depending on if the grouping defines a hierarchy or not. The most common ways to depict group structures are by using some visual node attributes such as color or by using an overlay to enclose the individual groups. Dynamic network visualization investigates the visualization of networks that change over time. Traditionally, such networks are described as a series of time slices. However, recently more research is being done on visualizing continuous and event-based networks. As time is a complex dimension, this should be taken into careful consideration when developing approaches here. There are certain dynamic aesthetic criteria that apply to develop effective visualization techniques. Dynamic networks are extended from general network visualization by considering the temporal aspect, essentially, putting networks in time. Multivariate networks are defined as an underlying network plus additional attributes attached to the nodes and / or edges. The main challenge is to represent both the underlying topology of the network and multiple attributes at the same time. We can arrive at this discipline by extending general network visualization to consider multiple attributes or variables. Geospatial networks are a subgroup of spatial networks, where the nodes and / or links may be associated with a geographic location. These are also one of the most popular networks, portraying financial and trade connections between countries or regions, or flight and shipping routes. This discipline extends general network visualization by attaching spatial or geographical information to the nodes or edges. The most common approach to depict this type of network is by overlaying the nodes and edges onto a cartographic map. Common scalability concerns in this network visualization discipline are mainly about node clutter and overlap, as well as edge crossings and overlaps, since the positions are constrained to a geographical location. However, there exist approaches that resolve these issues to some extent. A facet is defined as a specific aspect of the data. For example, spatio-temporal, multivariate, or grouping information. The discipline of multifaceted network visualization introduces specialized techniques to depict networks where one or more facets need to be displayed concurrently alongside the network's topology. The result, usually, incorporates aspects of the networked data that are considered distinct in other disciplines. Therefore, we can arrive to this discipline by extending general network visualization with techniques for encoding one or multiple facets. Furthermore, these facets also strongly inherit from other disciplines such as geospatial, group, multivariate, and dynamic network visualization, which is why they are all connected. Multi-layer networks are a discipline that considers depicting nodes that can belong to one or more layers. The semantics of a layer in this case depend heavily on the data structure and use case. For example, if we have multiple social media networks, such as Facebook, Twitter, LinkedIn, each of these can be considered a layer where the nodes have interlayer relationships to other people in that same network. We can also find overlaps between these networks, and such relationships can be modeled as intralayer relationships. We can arrive to this discipline by extending general network visualization to consider layer information associated with the node and slash or edges. The concept of multi-layer networks is also extended to consider different groupings, multiple variables, or dynamic data where each layer represents a specific group, attribute, or time slice. Now we move to the topic of task taxonomies. I will provide an overview of which task taxonomies exist and the disciplines they cover. Generally, from our literature search, we found that there are a lot less taxonomies compared to the number of surveys about different network visualization disciplines. A lot of disciplines are not covered by existing taxonomies, which makes it difficult to formally evaluate and compare techniques in these disciplines. We also noticed that for the existing taxonomies there is no clear relationship between them or the individual task classifications that they propose. So we classify the task taxonomies according to their support or coverage of a network visualization discipline as well as their individual task classifications. In the following, we go over the task taxonomies we found and describe their coverage. Meaning, if they are supported by existing taxonomies dedicated to the specific data type, or if higher-level abstract taxonomies can be extended to cover the specific discipline. To do this, we came up with two different kinds of supports. Specialized support refers to taxonomies that are explicitly designed for the target discipline. They are dedicated to network structures and specific data types. Generalized support refers to taxonomies that provide a categorization of tasks covering a broad range of data types. These can be used as a base for disciplines that lack a specialized taxonomy. These higher-level task taxonomies can be extended or adapted to consider network structures. Some of the higher-level visualization task taxonomies that have been used in the context of network visualization we found. Amar et al. That propose a framework for low-level analytical tasks generally for information visualization. Odryenko and Odryenko propose a framework of tasks for spatio-temporal data in exploratory analysis. Bremer and Munzner propose an abstract multi-level task typology of visualization tasks. Valiati et al. Propose a high-level task taxonomy for visualization tasks of multi-dimensional and multivariate data. Finally, Roth presents a task taxonomy for geovisualization and interactive cartography. Then the task taxonomies we found that are specific to network visualization and consider disciplines with unique data type characteristics are the following. For general network visualization, there are the task taxonomies by Lee et al. And Pandey et al. Socket et al. Propose a task taxonomy for group structures in network visualization. For dynamic network visualization, we have the most widespread support with 3 existing taxonomies. And et al. Propose a taxonomy of network evolution tasks. Bach et al. Propose tasks for supporting navigation in dynamic network visualization, and by Kara et al. Extend the framework by Arleo and Arleo to cover network-related tasks. Finally, for multivariate network visualization, we have the task taxonomy by Pretorius et al. We found that the remaining disciplines don't have a task taxonomy dedicated for their specific data type. This was also outlined in the respective surveys as an open challenge that should be addressed. We found no dedicated task taxonomy about large, geospatial, multifaceted, and multi-layer network visualization. So here is an overview of which disciplines have generalized and specialized support. In cases where there is no specialized support, we also add that there is currently no existing task taxonomy for these disciplines. However, even for the ones lacking a task taxonomy, we considered which general taxonomies may be extended and adapted to address this gap. As you can see, all disciplines can be supported to some extent by task taxonomies that offer generalized support. In most cases, these just do not address network structures and therefore need to be adapted. So now I want to discuss some of the results and takeaways from the surveys and task taxonomies and present our consolidation approach, as well as highlight gaps and saturated areas of research on these topics. Throughout the surveys we investigated, we discovered several inconsistencies between the terminology used in the classifications. There is also a large overlap in how the visualization techniques for different network visualization disciplines are described and categorized, but this does not become apparent. This motivated us to establish a common dictionary across network visualization disciplines and consolidate the terminology used. We classify the tags and keywords used to describe visualization approach us from individual surveys and group these into 6 higher-level categories. Here is an overview of our 6 high-level categories. In the paper we have this big table where each of the keywords and tags from the surveys is associated to our consolidated terminology. The table shows the higher-level categories as rows, with each having the list of consolidated terms belonging it, and the columns are the network visualization disciplines we identified. Each cell has the surveys that mention the terms by a categorization or list of keywords. Essentially, we are grouping together terms that refer to similar concepts from a visualization perspective or use different wording to describe this. This results in a heat map showing the more saturated and popular combinations, as well as areas that are under investigate. In the following, I will briefly go over some of the categories and list some examples of such inconsistencies. For more information and definitions, please check the paper as well as online supplementary material. These go into greater detail. So facet composition basically describes how a single or multiple facets of the data can be encoded alongside the network structure. There are multiple ways to achieve this, and we took inspiration from the work by Javed and Elmqvist about composite visualization and Gleicher about visual comparison for information visualization to identify and define different techniques to compose these facets alongside the network's representation. In this category, an example of how we grouped together different inconsistent terms would be the juxtaposition technique. In the literature, this is also referred to as static flip books, small multiples, multiple time slices. As these all encode the network in multiple snapshots and each has its own dedicated display space, this is the most common definition of juxtaposition. So we consolidated these terms under juxtaposition. Layouts are another category where we discovered a wide range of terms used to describe different categories of network layout algorithms. While there is a breadth of algorithms and techniques in literature that present different approaches to laying out a network, the terminology here used to describe these is also often inconsistent. For example, with energy-based approaches, the algorithms minimize an energy function in order to draw the network considering certain constraints or aesthetic criteria. The specific implementation details here vary widely, mostly in terms of what the energy function to be minimized is. In literature, these have been referred to as force-directed, spring embedder, and spring electrical layouting techniques, which all have the same thing in common. They attempt to minimize some kind of energy function. Therefore, we grouped all these terms under energy-based. Our consolidation resulted in a heat map of the most and least popular concepts in surveys on network visualization. By popular, I mean that these are the most or least widely used keywords and categories describing the network visualization techniques for a given discipline. From the consolidation, we notice that the most research is done on general network visualization, which is also the most dated discipline. In this discipline, the most common representations are node-link diagrams in a 2D context using energy-based layout techniques. Following up, the second most researched discipline is dynamic network visualization. Research in this discipline is focused on the composition of the network structure and the temporal facet. The most commonly used facet composition techniques are juxtaposition and animation. We also have somewhat of a balance between node-link and matrix representations. For node-link diagrams, the most commonly used layout technique is again an energy-based one. When we look at some of the least popular concepts in survey literature on network visualization, we can see that aesthetic criteria is a concept that is not thoroughly researched outside of the dynamic and general network visualization disciplines. This may suggest that there are either different aesthetic criteria that need to be taken into account for multivariate, multilayer, multifaceted, and group network visualization, or that since these disciplines stem from general network visualization, the concepts of aesthetic criteria are also valid here. Some interesting gaps in the survey literature we noticed are that while several surveys point out how tabular and matrix-based techniques are interesting and under-investigate, these are also not consistently experimented with across all disciplines. Furthermore, due to the increase in the complexity, heterogeneity, and size of networked data, we see opportunities for novel visualization techniques with regards to hybrid and alternative network representations. These may also overcome the traditional scalability concerns of standard and well-established approaches. Finally, even though uncertainty in networks is a topic that has been widely discussed across different surveys, it still presents an open challenge that is worth investigating. An aspect we wanted to investigate in our work related to the task taxonomies is the following. How do individual task taxonomies relate to each other, and what kind of overlaps exist between them in terms of their classifications? We derive a classification of tasks from literature aiming to consolidate and provide a high-level structure for tasks in different network visualization disciplines. Our task consolidation resulted in three main categories of tasks. Topology tasks. These are concerned with performing structural analysis on the individual entities of a network. Analytic activity tasks. These are higher-level analysis tasks that involve visually exploring and analyzing a dataset in order to extract knowledge or insights. And facet tasks describe operations that can be performed on individual facets of the network data. Here is an overview of our proposed task consolidation, along with the number of the task categories that map our consolidation. What we can see from this heat map is that operational tasks are not widely covered by existing taxonomies. Operational tasks are a part of the analytic activity that do not necessarily achieve a result in the analysis process, but rather supports all other tasks. Some examples could be reconfiguring a network visualization to depict a different aspect of the data or to fine-tune parameters or visualization properties. Then we can see that in terms of facet-related tasks, time, space, and group tasks are also not widely covered by existing taxonomies. Specifically for space or geospatial networks, there is a complete lack of a supporting taxonomy. These gaps present some interesting directions for future work. Finally, I want to talk a bit about some open challenges and interesting directions for future research we found and conclude this presentation. The first ongoing challenge, that I also believe is the most interesting, is that of novel visualization metaphors. Like I mentioned previously, the size, heterogeneity, and complexity of networks is ever increasing, and we are reaching limitations with standard approaches. Exploring new visualization modalities, metaphors for networks, and alternative or hybrid approaches has the potential of overcoming these limitations, although potentially associated with a steeper learning curve. Another major ongoing challenge concerns evaluation methodologies, and this is also highly related to the availability of task taxonomies for some disciplines, specifically those that lack a specialized support. Since task taxonomies support the formal evaluation and comparison of techniques for network visualization, when there is no available taxonomy, it gets a bit harder to compare two different approaches for the same set of tasks, since in their evaluation there might not be an overlap. Filling these gaps would facilitate more comparable evaluations. Furthermore, several surveys advocate for surpassing traditional performance metrics, such as error rates and response times, since these may not be descriptive enough in order to determine the value of a visualization. They propose to consider metrics, such as the cognitive aspects, perception issues, and user engagement associated with these approaches to facilitate the navigation, exploration, and interaction with networks are highlighted by a number of surveys as an ongoing challenge. Since there is no classification or survey on interaction techniques for network visualization, this may be an interesting direction for future research. Additionally, interactions to support human-assisted analysis could be interesting, such as combining domain expert knowledge with automated analysis techniques. Finally, collaborative analysis is something that has been gaining traction recently. This has big potential moving forward, considering the large and multimodal networks. Collaborative analysis emphasizes the need for a shared understanding and effective communication among collaborators. Visualization plays a crucial role in facilitating this by providing a representation of networks that can be easily interpreted and discussed by the team members. The visualization should support interactive exploration, annotation, and sharing to enable collaborative sense-making. This can include features like shared views, synchronous or asynchronous discussions, and real-time updates to the visualization as changes are made by different collaborators. So summarizing, we presented our meta-survey on the field of network visualization, focusing on survey and task taxonomy literature. We consolidated terminology and classifications from surveys, as well as task taxonomies, to provide an overview of more saturated and less popular areas of research. This led us to identifying interesting directions for future work. Our meta-survey shows the significant breadth of concepts, terminology, and research related to network visualization. We consider taking a step back and reassessing the problem from a broader perspective. As this field begins to face the challenges offered by machine learning and immersive analytics, unifying existing research would increase awareness and knowledge. Our roadmap is intended as a first step in this direction. And coming back to our overarching question, are we there yet? Well, no, we are not really there yet. There are still a lot of open challenges and gaps in literature worth pursuing. This concludes my talk. Thank you for your attention. You can find our paper by scanning the QR code and my contact info as well.